In 1913, Niels Bohr proposed an atomic model that quantitatively explained the features of the structure of hydrogen atom and its spectrum. The postulates of it describe motion of electrons in a stationary orbit, fixed energy of electrons, energy change during transition of electrons, and fixed angular momentum of electrons. The first postulate states that the electron in the hydrogen atom can move around the nucleus in circular paths of fixed radius and energy called orbits. Orbits are arranged concentrically around the nucleus and are also called stationary states or allowed energy states. Electrons are held by the nucleus in orbits by a strong electrostatic force. According to the second postulate, the energy of an electron in the orbit remains constant until the electron absorbs energy to jump to a higher orbit, or releases energy to move to a lower orbit. So each emission or absorption of radiation energy represents the electron's transition from one stationary orbit to another. The energy difference between the two orbits is given by equation delta E is equal to E final minus E initial. The third postulate states that the frequency of the radiation emitted or absorbed can be represented by the equation nu is equal to delta E divided by H. That is, E2 minus E1 divided by H, where E1 and E2 are the energies of the lower and higher stationary states, and H is the Planck's constant. The fourth postulate states that an electron moving in a circular orbit has an angular momentum equal to the product of its mass me, linear velocity v, and radius of orbit r, which can be expressed as an integral multiple of h divided by 2 pi, where n is an integer that has the values 1, 2, 3, and so on, and h is the Planck's constant. Since angular momentum can only be an integral multiple of h divided by 2 pi, only certain fixed orbits or stationary states are allowed for electrons to move around the nucleus. Let us now get into more details of Bohr's theory of hydrogen atom. According to Bohr's theory, the stationary states for electron are numbered n is equal to 1, 2, 3, and so on. These integral numbers are called principal quantum numbers. The radii of stationary states or orbits can be given by the expression. Radius of the nth orbit, Rn, is equal to n square multiplied by the constant A0, which is equal to 52.9 picometer. This means that the smallest possible value of r, or the radius of the very first orbit, where the sole electron of the hydrogen atom found in its ground state is equal to 52.9 picometer. This radius is called Bohr's radius. The energy of a stationary state or orbit is given by the equation. Energy of the nth orbit, En, is equal to minus Rh multiplied by 1 divided by n square, where n is the principal quantum number of the orbit and Rh is Rydberg's constant, whose value is 2.18 multiplied by 10 raised to the power minus 18 joules. Energy of nth orbit of a hydrogen atom in electron volts is equal to minus 13.6 divided by n square. Thus, the energy of the ground state, n is equal to 1, for hydrogen atom is equal to minus 2.18 multiplied by 10 raised to the power minus 18 joules. The energies of excited states can be measured in the same way and represented in the form of an energy level diagram. Note that the energy of the stationary state, n equal to infinity, is 0. At this energy level, the electron is completely free from the influence of nucleus. In other words, the hydrogen atom is said to be ionized. An electron emits energy as it approaches towards the nucleus, and hence its energy decreases with decrease in distance between it and the nucleus. This principle accounts for the negative sign of energies of electrons in various orbits. Bohr's theory also applies to other ions which are isoelectronic with hydrogen, such as helium plus, lithium 2 plus, and beryllium 3 plus ions that contain 1 electron each. The energies of the stationary states of hydrogen-like species are given by the expression En is equal to minus Rydberg constant multiplied by the square of atomic number divided by the square of principal quantum number. The orbit radii of these ions is given by the expression Rn equal to Bohr's radius multiplied by the square of principal quantum number divided by the atomic number. From the orbit energies and radii equations of hydrogen-like ions, it can be deduced that with increase in Z, the value of energy becomes more negative and the radius becomes smaller. Bohr's theory also states that the magnitude of velocity of electron increases with increase of positive charge on the nucleus, that is, increase of atomic number, and decreases with increase of principal quantum number. Although Bohr's theory is not based on the modern quantum mechanics, it helps to resolve many questions related with atomic structure and spectra. For example, it provides explanation for main limitation of Rutherford's model, the stability of an atom. According to Bohr's model, electrons are held in stationary orbits by virtue of an electrostatic force. That's why they don't fall into the nucleus. The model also stated that electrons are distributed in concentric orbits around the nucleus. The orbits have a specific energy, which decreases or increases during the electronic transition. In addition, it helps to quantitatively explain the emission and absorption line spectrums of hydrogen and hydrogen-like species. Let's see how. According to the second postulate of Bohr's model, the energy gap between the two orbits is given by the equation delta E equals to E final minus E initial. Since the energy of a stationary state is given by the equation En is equal to minus of Rydberg's constant multiplied by 1 divided by n square, we can substitute E final in the energy change equation by minus RH divided by n final square and E initial by minus RH divided by n initial square to get an equation similar to the expression used by Rydberg. Note that in case of absorption of energy, delta E is positive, and in case of emission, delta E is negative. Thus, each spectral line in absorption or emission spectrum can be associated to transition of states by the electron of a particular hydrogen atom. Bohr's model also shows that the intensity of each spectral line depends upon the frequency or wavelength of photons absorbed or emitted. Because of the presence of multiple hydrogen atoms, a large number of spectral lines are observed. The frequency associated with the absorption and emission of the photon can be calculated using the equation delta E divided by h, where h is the Planck's constant. The wavelength can be calculated by dividing the velocity of electron with the frequency of the radiation. The more the number of photons of a particular frequency or wavelength absorbed or emitted, the more the intensity of the associated spectral line. Bohr's atomic model of hydrogen atom, therefore, helps to get most of the answers to the questions prevalent at that time. However, it could not explain the line spectrum of multi-electron atoms. Presence of doublets in the hydrogen spectrum when observed through sophisticated spectroscopes. The splitting of spectral lines in the presence of magnetic field, a phenomenon called Zeeman effect. The splitting of spectral lines in the presence of electric field, a phenomenon called Stark effect. The ability of atoms to form molecules through chemical bonding. And the dual nature of electrons, both as wave and particle. It contradicts Heisenberg's uncertainty principle, which says that it is possible to determine both the position and velocity of an electron simultaneously and accurately. Two important developments that questioned the rationality of Bohr's model are: 1. Dual behavior of matter, and 2. Heisenberg uncertainty principle. Let's understand these developments in detail. After the dual behavior of electromagnetic radiation was known, de Broglie proposed in 1924 that all matter has wave and particle-like properties. His theory implied that just like photons, every moving object, be it an electron, a ball, or a planet, has a wave nature. He also gave the relation between wavelength and momentum of a material particle based on the energy equations of photons in their wave and particle forms. A photon displaying wave character has energy equal to h multiplied by nu. A photon having a particle character has energy equal to m multiplied by c raised to the power 2. By combining these two equations and replacing nu with c by lambda, we get lambda is equal to h divided by mc. To generalize the equation for any material particle, c, the velocity of light is replaced with v, the velocity of the material particle. The resultant equation is called de Broglie's equation. Since the momentum of a particle is the product of its mass and velocity, the relation between wavelength and momentum of a material particle can be given by de Broglie's equation. It can be noted from de Broglie's equation that the wavelength and mass of an object are inversely proportional. That is, that the wavelength of heavier objects is small and vice versa. Thus, the wavelength of lighter particles like electrons can be measured experimentally, whereas that of heavier objects like a ball or a planet cannot be detected. De Broglie's theory and equation was later proved to be correct when it was found that an electron beam undergoes diffraction, a property that is unique to waves. The wave nature of electron forms the basis of an electron microscope that achieves a magnification of about 15 million times, and is therefore a powerful tool in modern scientific research. Let's now look at the Heisenberg uncertainty principle. In 1927, a German physicist, Werner Heisenberg, took forward the concept of dual behavior of matter and radiation to give a principle about the uncertainties in simultaneous measurements of position and momentum of small particles. He proposed that it is impossible to measure simultaneously and accurately the exact position and momentum of a small particle like an electron. Mathematically, Heisenberg's uncertainty principle can be expressed with the equation delta x multiplied by delta px is greater than or equal to h divided by 4 pi, where delta x is the uncertainty in position and delta px is the uncertainty in the momentum of the particle. This equation can also be expressed in terms of mass and velocity of the particle. Note that the uncertainty in the position and velocity are inversely proportional to each other. This means that if the position of the electron is known with high degree of accuracy, then the velocity of the electron will be uncertain and vice versa. Also note that the uncertainty in the position and velocity are inversely proportional to the mass of the object. That is, uncertainty in the position and velocity decreases as the mass of the object increases and vice versa. For example, if the uncertainty principle is applied to a macroscopic object, an object weighing a milligram 10 to the power 6 kg, the value of the product of delta V and delta X is extremely small. Therefore, the associated uncertainty is also insignificant. On applying this uncertainty principle to a microscopic particle, like an electron having mass equal to 9.1 multiplied by 10 to the power minus 31, we find that the product of delta V and delta X is significant enough and therefore cannot be ignored. Hence, we see that Heisenberg's uncertainty principle also holds significance only for motion of microscopic particles and not for macroscopic objects. The position of an electron can be determined experimentally by illuminating it with electromagnetic radiation having a wavelength smaller than the dimensions of an electron. However, the velocity of an illuminated electron cannot be detected as the high momentum photons of the light increase the energy of electrons by collisions. As we have already calculated that for an electron, the product of delta X and delta V is found to be equal to 10 raised to the power minus 4 square meters per second. Therefore, the uncertainty in velocity can be calculated by substituting the value for delta X, say 10 to the power minus 8 meters, in the Heisenberg's equation. This means that if one tries to find the exact location of the electron to an uncertainty of only 10 to the power minus 8 meters, the uncertainty in velocity becomes positive and enormously significant. This value of uncertainty in velocity is so big that the classical picture of electrons moving in Bohr's orbits becomes unrealistic. As it is impossible to determine simultaneously and accurately the position and velocity for an electron at any given instant, it is not possible to talk about the trajectory of an electron. Thus, Bohr's model not only ignores dual nature of matter, but also contradicts the Heisenberg's uncertainty principle. Due to these inherent weaknesses in the Bohr's model, a need for such an atomic model arose which could account not only for the dual nature of electrons, but also be consistent with the Heisenberg uncertainty principle. This search led to the advent of quantum mechanics. The de Broglie's dual behavior of matter and Heisenberg's uncertainty principle gave birth to a completely new branch of science called quantum mechanics. Classical mechanics successfully explains the behavior of macroscopic objects, such as falling stone, on the basis of particle nature. It ignores the concept of the dual behavior of matter and thus fails to explain the behavior of microscopic particles, such as protons, electrons, and so on. On the other hand, as quantum mechanics is based on the wave properties of matter, it describes the behavior of microscopic particles in a much better way. Hence, quantum mechanics is a theoretical science that helps to study the motions of the microscopic objects that have observable wave-like and particle-like properties. Quantum mechanics was developed independently by Werner Heisenberg and Erwin Schrödinger in 1926. The fundamental equation in quantum mechanics is Schrödinger's wave equation. In quantum mechanics, the mathematical expression which describes the wave motion associated with a particle is popularly known as Schrödinger wave equation. It gives the probability of finding an electron at different points in an atom. The Schrödinger's wave equation is obtained by differentiating the equation for the standing wave of an electron in the hydrogen atom. In short, Schrödinger wave equation is written in terms of Hamiltonian operator as shown here. In this equation, E stands for total energy of the system, which includes kinetic energies of all the subatomic particles and potential energy due to attractive and repulsive forces operating in an atom. When Schrödinger wave equation is solved for an electron of an atom, such as hydrogen atom, it gives the values of the possible energy levels in which the electron can move, called quantized energy states, as well as the wave functions corresponding to these energy levels. Note that, in quantum mechanics, all the properties of a system are expressed in terms of a wave function. This is obtained by solving the Schrödinger's equation. The wave function, psi, is a mathematical function that represents amplitude of the wave. It does not carry any physical significance. Therefore, the square of the amplitude of electron wave, that is, psi square, gives the probability of finding the electron at a point within an atom. That is why the function psi square is called probability density and is always positive. By finding the probability density at different points in an atom, one can predict the region of space around the nucleus, within which the probability of finding the electron is the maximum. This three-dimensional space around the nucleus, where the probability of finding the electron is maximum, is called orbital. This is why the wave function for an electron in an atom is also called orbital wave function or atomic orbital. An electron can have multiple wave functions and therefore multiple atomic orbitals. Schrödinger wave equation can successfully explain all aspects of hydrogen and hydrogen-like species It, however, cannot be completely solved for multi-electron atoms. Such calculations show that the orbitals of multi-electron atoms are similar to the orbitals of hydrogen atom in most aspects. The principal difference between the orbitals of single electron atoms and the orbitals of multiple electron atoms is that the orbitals of multi-electron atoms are contracted due to increased nuclear charge. In addition, unlike orbitals of hydrogen or hydrogen-like atoms, whose energies depend only on the principal quantum number, the orbital energies in multi-electron atoms also depend on azimuthal quantum number, in addition to principal quantum number. Let us now move on to certain other important aspects of the quantum mechanical model of atom. According to this model, electrons can only have specific values of energy, which means that the energy of electrons are quantized. The quantized energy values that result from the wave-like properties of electrons can be calculated along with the associated wave functions, psi, using the Schrödinger wave equation. The quantum mechanical model of atom supports the Heisenberg's uncertainty principle and says that one can only determine the probability of finding an electron at different points in the atom, but not its exact path. The atomic orbital for the electron is given by its orbital wave function psi. There are multiple atomic orbitals in an atom, as an electron can have many wave functions, each of which contains a maximum of 2 electrons. In a multi-electron atom, the electrons are filled in various orbitals in the order of increasing energy. Note that these orbits are two-dimensional circular paths around the nucleus, in which the electrons revolve, whereas atomic orbitals are three-dimensional regions around the nucleus where the probability of finding an electron is the maximum. Now let us see how the atomic orbitals are distinguished by quantum numbers. On solving Schrödinger wave equation for hydrogen atom, the solution gives quantized energy states and the wave functions which are characterized by a set of 3 quantum numbers, which are the principal quantum number, the azimuthal quantum number, and the magnetic quantum number. An atomic orbital of an atom is characterized by these 3 set of quantum numbers. Orbitals are distinguished from each other on the basis of shape, size, and orientation. The probability of finding an electron depends on these 3 distinguishing characteristics. Such orbitals are again distinguished by 3 quantum numbers, which are, again, the principal quantum number, the azimuthal quantum number, and the magnetic quantum number. A 4th quantum number, called the spin quantum number, was also introduced later to represent the spin of the electron about its axis. Spin quantum number is characteristic for an electron. Therefore, quantum numbers can be defined as a set of 4 numbers that provide the complete information about the electrons in an atom. Let's understand these quantum numbers in detail. The principal quantum number, denoted by the letter n, determines the size and, to a large extent, the energy of the orbital in which the electron resides. The size of an orbital increases with the increase in n. In other words, the larger the value of n, the greater is the distance of the electron from the nucleus. An electron needs energy to move to the higher energy levels as it has to overcome the forces of attraction from the nucleus. Hence, the energy of an orbital increases with the increase in n. Note that for hydrogen and hydrogen-like species, energy as well as the size of an orbital depends only on n. In addition, with the increase in the value of n, the number of allowed orbitals increases and are given by n square. Shells are denoted by the capital letters K, L, M, N, and so on for the values of n equal to 1, 2, 3, 4, and so on respectively. The number of electrons in a shell is given by 2n square. Therefore, for n equal to 1, there will be 2 electrons in the K shell, and for n equal to 2, there will be 8 electrons in the L shell. The number of electrons in M and N shells will be 18 and 32 respectively. As the energy increases with the increase in n, the energies of the various shells follow the sequence K less than L less than M less than N less than, and so on. Let us move on to the next quantum number, that is, the azimuthal quantum number. It is denoted by the letter L. The number of subshells is given by the azimuthal quantum number. The azimuthal quantum number is also known as the orbital angular momentum or subsidiary quantum number. The azimuthal quantum number also describes the three-dimensional shapes of orbitals that you will learn about in the next module. For a given value of the principal quantum number n, the azimuthal quantum number L can have n values ranging from 0 to n-1. The value of L, in turn, defines the number of subshells, which means that when n is equal to 1, L is equal to 0. That is, there is only one subshell in first main energy level. Similarly, for n is equal to 2, L is equal to 0 and 1. That is, there are two subshells in second main energy level. And for n is equal to 3, L is equal to 0, 1, 2. That is, there are three subshells in third main energy level. Subshells corresponding to different values of L, that is, 0, 1, 2, 3, 4, are represented by the symbols S, P, D, F, G, and so on. The first four notations are the initial letters of the words sharp, principal, diffused, and fundamental, the words formerly used to describe different spectral lines. Thus, the subshells in the K shell for n is equal to 1 is S. In the L shell with n is equal to 2 are S, P. In the M shell for n is equal to 3 are S, P, D. In the N shell for n is equal to 4 are S, P, D, F, and so on. The S subshell has the lowest energy, and the energies of the subshells within the same principal shell follow the order S less than P less than D less than F. An electron moving in a subshell generates an electric field and magnetic field resulting from its motion around the nucleus. Thus, under the influence of an external magnetic field, the electrons moving in the subshells tend to reorient themselves into the specific orbitals. The number of preferred orientations of electrons belonging to a subshell is given by another quantum number called the magnetic orbital quantum number ML. Each orientation corresponds to an orbital. Therefore, magnetic quantum number helps to determine the number of orbitals within each subshell. For a subshell, there can be a maximum of 2L plus 1 preferred orientations or orbitals with values ranging from -L to +L, including 0. Hence, for L is equal to 0, the number of preferred orientations is equal to 1. Thus, S subshell can have only one orientation in space and only one orbital. For L is equal to 1, the P subshell can have a maximum of 3 orbitals with orientations along the 3 axes. Similarly, for L is equal to 2, D subshell has 5 preferred orientations and hence 5 orbitals. Using the same calculation, F, G and H subshells can have 7, 9 and 11 orbitals each. Note that all orbitals belonging to a subshell have the same energies and therefore are called degenerate orbitals. Thus, the 3 quantum numbers can very well define the energy, shape and orientation of atomic orbitals. However, these quantum numbers fail to explain the presence of closely spaced lines, doublets or triplets in the atomic spectra of multi-electron atoms. To explain these lines, in the year 1925, George O. Beck and Samuel Goudsmit introduced the 4th quantum number called the electron spin quantum number or MS. The two scientists suggested that just like the planet Earth, an electron rotates around its own axis while revolving around the nucleus. The electron spin results in an intrinsic spin angular momentum that can have 2 possible orientations, clockwise or anti-clockwise, relative to the chosen axis. These orientations are defined by the spin quantum number ms that can take the values of +1/2 and -1/2. These values are represented by upward and downward arrows and are called spin up and spin down respectively. The 2 electrons belonging to a particular orbital always have opposite spins. We have already learned that in quantum mechanics, all the properties of a system are expressed in terms of a wave function. This is obtained by solving the Schrödinger's equation. The wave function, psi, is a mathematical function that represents amplitude of the wave. It does not carry any physical significance. Therefore, the square of the amplitude of electron wave, that is, psi square, gives the probability of finding the electron at a point within an atom. This is predicted by German physicist Max Born. That is why the function psi square is called probability density, and is always positive. By finding the probability density at different points in an atom, one can predict the region of space around the nucleus, within which the probability of finding the electron is the maximum. This three-dimensional space around the nucleus, where the probability of finding the electron is maximum, is called orbital. The probability of finding an electron is a function of distance r from the nucleus. The probability of finding an electron at a distance from the nucleus is called radial probability distribution. Let us look at the plots corresponding to the orbital wave function psi as a function of distance of an electron from the nucleus, that is, r, for the 1s and 2s orbitals. Similarly, look at the curves of probability density psi square as a function of radius for these orbitals. The following are the important conclusions that can be drawn from these plots. At r equals 0 or infinity, that is, at the nucleus or at infinite distance from the nucleus, the probability of finding an electron is 0. The peak of the curve indicates that the probability of finding the electron at this distance is maximum. For s orbitals, the number of peaks obtained in the plots is equal to the n value. Hence, for 1s and 2s orbitals, the number of peaks obtained are 1 and 2 respectively. For 1s orbital, the probability density is found to be the maximum in the vicinity of the nucleus and decreases sharply as the distance from the nucleus increases. On the contrary, for 2s orbital, the probability density first decreases sharply to 0 and then increases to reach a small maxima before it drops again to 0 with the increasing value of the radius. The region where the probability density function reduces to 0 is called radial nodes or nodal surfaces or nodes. For s orbitals, the number of radial nodes increases with the value of the principal quantum number n, and found to be equal to n-1. Therefore, 1s orbital does not show any nodes, whereas 2s and 3s orbitals show 1 and 2 nodes respectively. Probability density of electrons can be depicted with the help of the charge cloud concept or charge cloud diagrams. In this, the cloud of negative charge is represented by means of dots. Note that a dot represents the location of the electron at a given point of time. The cloud of negative charge is denser in certain parts than others. This indicates that the probability of finding the electron is maximum in that region. On the other hand, the probability of finding an electron in a particular direction or angle is called angular probability distribution. The probability of finding an electron in a particular direction or angle can be depicted by boundary surface diagrams. The boundary is drawn where the probability density remains fairly constant. The region inside the boundary surface depicts the orbital where the probability of finding an electron is maximum, that is, about 90%. The boundary surface diagrams define the shapes of various orbitals. Therefore, the shape of the electron cloud density and that of boundary surface determines the shape of the orbital. The boundary surface diagram for s orbital is always a sphere centered on the nucleus, irrespective of the principal shell to which the orbital belongs. This is because, for a given value of radius, the probability of finding the electron in the s orbital of a principal shell is found to be identical in all directions. Therefore, the shape of s orbital is a symmetric sphere. Note that, although all s orbitals are symmetrically spherical, the shapes of the s orbital belonging to different principal shells differ in two aspects. 1. The number of nodes, and 2. Size and energy. As the size and energy of the principal shells increases with increase in the value of n, their orbitals also follow the same trend. For example, the size and energy of 4s is greater than 3s, followed by 2s, and then 1s. Let us now discuss the shape and orientation of p orbitals. The boundary surface diagram for the p orbital indicates the presence of two lobes that lie on either side of the plane that passes through the nucleus, giving a dumbbell shape to the p orbital. The shape suggests that the probability of finding the p electrons is the maximum within the two lobes. The probability density function is 0 on the plane where the two lobes touch each other. Since the azimuthal quantum number L is equal to 1 for p orbital, the magnetic quantum number ML has values -1, 0, and +1, which represent three different orientations for p orbitals along the three axes, x, y, and z respectively. Hence, there are three p orbitals which lie perpendicular to each other. Irrespective of the direction at which the electron density lies, the size, shape, and energy of these three orbitals belonging to the same principal shell is identical. However, like s orbitals, the size and energy of p orbitals increases with increase in the principal quantum number. For example, the size and energy of 5p is greater than 4p, which in turn is greater than 3p, followed by 2p as shown. The number of radial nodes for p orbitals is given by the expression n-2. Therefore, number of radial nodes is 0 for 2p orbital, 1 for 3p orbital, 2 for 4p orbital, and so on. In addition to these radial nodes, for np and nd orbitals, the probability density function is also 0 at planes passing through the nucleus. These planes are called nodal planes. Number of nodal planes for a p orbital is 1. That is, the plane which passes through the origin at which electron probability of finding an electron is 0 is called a nodal plane. For example, the nodal plane for py orbital lies along xz plane. Nodal plane is also called angular node, and number of angular nodes for a p orbital is equal to the value of azimuthal quantum number L. For the d orbital, the azimuthal quantum number L is equal to 2. Therefore, the number of possible orientations given by the magnetic quantum number ML is 5, corresponding to ML is equal to -2, -1, 0, +1, +2. The boundary surface diagrams pertaining to these orientations, designated as dxy, dyz, dxz, dx square minus y square, and dz square are shown. Note the similarity in shapes of the first 4 d orbitals, which are different from the 5th orbital dz square. The shape of dz square is donut shape. All the 5 d orbitals belonging to a principal shell have the same energies. The size and energies increase with increase in the principal quantum number. For example, the order of the size and energy of various d orbitals is 5d greater than 4d, which in turn is greater than 3d. The number of radial nodes for d orbitals is given by the expression n-3. Therefore, the number of radial nodes is 0 for 3d orbital, 1 for 4d orbital, and so on. On the other hand, the number of angular nodes is equal to the value of L, that is 2. Hence, 2 angular nodes exist for a d orbital. For example, for dxz orbital, there are 2 nodal planes passing through the origin and bisecting the xz plane containing y-axis. Note that the total number of nodes for an orbital is given by the expression n-1. The total number of nodes is equal to sum of angular nodes given by L and radial nodes given by n-L-1 respectively. For example, let us calculate the total number of nodes for 3D, which is given by the expression n-1. As the value of n is equal to 3, by substituting the value of n in this expression, we get the total number of nodes 2. The value of L for d orbital is 2, and hence the numbers of angular nodes are 2 for 3d. As the value of n is equal to 3, the number of radial nodes as per the formula is equal to 0. Let's now have a detailed look at the energies of orbitals. As stated earlier, in general, the energy of the orbitals increases with the principal quantum number, and the energies of all the orbitals belonging to a subshell remains the same in the ground state. For single electron systems, such as hydrogen and other isoelectronic species, such as unipositive helium ion and dipositive lithium ion, the energies of all the orbitals for a given value of n are the same, irrespective of their subshell in which it is present, s, p, d, or f. That is, the energy of an electron exclusively depends on principal quantum number and not on azimuthal quantum number. For example, the energy of an electron present in 3s, 3p, or 3d remains the same, irrespective of it having different values of azimuthal quantum number. 1s in the hydrogen atom represents the most stable state for the sole electron and is called the ground state. The energy states with n greater than 1 represent the excited states for the electron in the hydrogen atom. Unlike the single electron species, the energy of an electron in a multi-electron atom depends on azimuthal quantum number, also in addition to principal quantum number. This essentially means that for a given value of n, the orbitals s, p, d, f possess different energies for different azimuthal quantum numbers. Let us look at the energy level diagrams for hydrogen atom and multi-electron atom, which depicts the arrangement of various orbitals. Now, let us understand why in case of a multi-electron atom, the energies of different orbitals of a given principal shell possess different energies in contrary to hydrogen atom. In a multi-electron atom, the different energies of different orbitals of a given principal shell is attributed to the inter-electronic repulsions among the electrons present. On the other hand, in hydrogen atom, due to the presence of only one electron, the only electrical interaction present is the electrostatic forces of attraction between the nucleus and the electron. Hence, in hydrogen atom, the subshells belonging to the same principal shell have same energy. Despite these repulsive interactions, the multi-electron atoms are as stable as the hydrogen atom because the net attractive interactions between these electrons and the nucleus are more than the repulsive interactions among the electrons. The attractive interactions of an electron increases with increase in positive charge on the nucleus. The complete attractive interactions of the positive charge are not experienced by the outermost electrons, as the electrons in the inner shells tend to shield the electrons in the outer shells from positive attraction of nucleus. Thus, the net positive charge experienced by the outermost electrons from the nucleus is called effective nuclear charge, and the shielding of outermost electrons from the attractive forces of nucleus by the inner shell electrons is called shielding effect or screening effect. Despite of the shielding effect, the net attractive force experienced by the outer shell electrons increases with increase in nuclear charge. In other words, the energy of interaction between nucleus and electron, that is, orbital energy, decreases or becomes more negative with increase in atomic number. The energies of the orbitals in the same subshell decrease with increase in the atomic number or effective nuclear charge. For example, energy of 2s orbital of hydrogen atom is greater than that of 2s orbital of helium, and that of helium is greater than that of lithium, and so on. That is, E2SH greater than E2SHe greater than E2SLi. The attractive and repulsive interactions in a multi-electron atom depend upon the shape of the orbital and shell. As the shape of s orbital is spherical, it shields the electrons more effectively as compared to p or d orbitals present in the same shell. In addition, due to spherical shape, the electron in the s orbital spends more time closer to the nucleus in comparison to p orbital. Similarly, the electrons in the p orbital spend more time closer to the nucleus in comparison to d orbital. This is due to the difference in the shape of their orbitals. Since the shape of the orbitals is defined by azimuthal quantum number L, we can say that the effective nuclear charge experienced by the orbital decreases with increase in the value of L. Therefore, s orbital with L equal to 0 is more tightly bound to the nucleus as compared to p orbital with L equal to 1 and d orbital with L equal to 2. Due to the difference in the net effective nuclear charge experienced by different orbitals of a principal shell, the degeneracy is lost and hence they show different energies. Because the effective nuclear charge experienced by the orbitals decreases with increase in L, the energy of s orbital is lower than that of p orbital, and that of p orbital is lesser than d orbital and so on. With the increase in shell number n, the energy of the orbitals also increases. As a generic guideline, the lower the value of n plus L for an orbital, the lower is its energy. This explains why 4s possess lesser energy than the 3d orbital. If two orbitals have the same value of n plus L, for example, 2p and 3s orbitals, the orbital with lower value of n, that is 2p, will have the lower energy. The filling of electrons into the orbitals of an atom is governed by the Aufbau principle, Pauli's exclusion principle, and Hund's rule of maximum multiplicity. Let us start with Aufbau principle. Aufbau is a German word which means building up or construction. Here, building up refers to the sequence in which the electrons enter into various atomic orbitals. This principle states that, in the ground state of the atoms, the orbitals are filled in the order of their increasing energies. This means that electrons first occupy the lowest energy orbitals available to them, and then enter into the higher energy orbitals successively. The order in which the various orbitals are filled is 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, and so on. This order can be represented in the form of a diagram as shown here, in which the direction of arrows indicate the order of filling of the orbitals. This representation can be conveniently remembered. The energy of an orbital is determined by using the n plus L rule. According to this rule, the lower the value of n plus L for an orbital, the lower is its energy. If two orbitals have the same n plus L value, the orbital with lower value of n has lower energy and hence is filled first. For example, for 4s orbital, the value of n and L are 4 and 0 respectively. Hence, the n plus L value of 4 plus 0 equal to 4. For third orbital, the value of n and L are 3 and 2 respectively. Hence, the n plus L value is 3 plus 2 equal to 5. This shows that the 4s orbital will be filled first, as the 4s orbital has lower value of n plus L than the third orbital has. The orbitals 2p and 3s have same value of n plus L, which is 3. Now, as per the n plus L rule, the orbital with the lower value of n has lower energy and hence is filled first. Thus, 2p is filled first, followed by 3s. Let us observe the arrangement of orbitals up to 4p in increasing order in accordance to the n plus L rule in the following given table. Next, let us move on to Pauli's exclusion principle. Austrian scientist Wolfgang Pauli has put forward the principle called Pauli's exclusion principle. This exclusion principle provides certain restrictions for the number of electrons to be filled in various orbitals. The Pauli's exclusion principle states that no two electrons in an atom can have the same set of 4 quantum numbers. This principle can also be stated as only 2 electrons may exist in the same orbital, and these electrons must have the opposite spin. This means that 2 electrons in an atom can have a maximum of 3 quantum numbers that are same with each other but not all the 4. Note that if one electron spins in clockwise direction, the other electron spins in anti-clockwise direction. Let us write the values of 4 set of quantum numbers for 2 electrons in 1s orbital. As shown here, the values of n, l, m and s for the first electron are 1, 0, 0 and plus half. The values for the second electron are 1, 0, 0 and minus half. This shows that the 2 electrons have the same values for n, l and m, but different values for s. This indicates that the maximum number of electrons that can be accommodated in an orbital is 2. Similarly, as p, d and f subshells have 3, 5 and 7 orbitals, they can have the maximum number of electrons equal to 6, 10 and 14 respectively. We know that the total number of subshells that can be present in a shell is equal to the value of n, which is the principal quantum number. This principle has an immense value as it gives the maximum number of electrons that can be accommodated in a shell, which is equal to 2n square. For example, if the value of n is 2, the total number of electrons can be calculated by substituting the value of n into n square, which is equal to 2 multiplied by 2 square, which is equal to 8. The third rule of filling of electrons into the orbitals was proposed by Friedrich Hund. It is called the Hund's rule of maximum multiplicity. This rule helps in filling of electrons into the orbitals of same subshell. The orbitals belonging to the same subshell have same energy and are called degenerate orbitals. The Hund's rule of maximum multiplicity states that in a set of degenerate orbitals, the orbitals are singly occupied first and then pairing of electrons takes place. It can also be stated as the pairing of electrons in the orbitals belonging to the same subshell doesn't take place until each orbital belonging to the same subshell gets 1 electron each. Therefore, electron pairing in p, d or f subshells cannot take place until each orbital of a given subshell contains 1 electron each. In other words, pairing of electrons in p, d and f subshells starts with the 4th, 6th and 8th electron respectively, as shown here. Also, all the singly occupied orbitals will have spins in the same direction. Moreover, it is observed that half-filled and completely filled subshells impart greater stability to atoms due to the symmetrical distribution of electrons. More detailed explanation on the cause of stability of half-filled and completely filled subshells will be learnt in the later part. We can define electronic configuration as the distribution of electrons into various orbitals of an atom. Before we begin to understand the electronic configuration of atoms, let's recap the 3 main principles that guide the filling of electrons into various orbitals in an atom. First is the Aufbau principle. It states that In the ground state of the atoms, the orbitals are filled in order of their increasing energies. In other words, electrons first occupy the lowest energy orbital and then enter into successive higher energy orbitals. The electrons enter into various orbitals in an increasing order of n plus L value. Second is the Pauli's exclusion principle. It states that an orbital can have maximum 2 electrons and these must have opposite spins. And finally, the Hund's rule of maximum multiplicity that deals with filling of electrons into equal energy orbitals of the same subshell. It states that electron pairing in p, d and f orbitals cannot occur until each orbital of a given subshell contains 1 electron each or is singly occupied. We can represent the electronic configuration in 2 ways. One way is to represent it by the orbital diagram method. In this method, the orbital is represented by a box and an electron is represented by an arrow in it. If the spin of the electron is in a clockwise direction, then the head of the arrow points upwards. If the spin is in an anti-clockwise direction, then the head of the arrow points downwards. A clockwise spin is called the positive spin, and anti-clockwise spin, it is called the negative spin. The other way of representing the electronic configuration is by the NLX method. Here, N represents the number of the principal shell, that is 1, 2, 3, etc. L represents any subshell or any orbital. S, P, D, F and X represents the number of electrons present in that orbital. For example, 3p2 denotes that the p subshell of the third principal orbit contains 2 electrons. Now let's discuss the electronic configuration of the first 10 elements: hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Hydrogen has only 1 electron which must be filled in the orbital of lowest energy, that is 1s. Helium has 2 electrons. Both these electrons can be filled into the s orbital. However, according to Pauli's exclusion principle, these 2 electrons should have opposite spins. Lithium has 3 electrons. 2 electrons will fill the s orbital, while the remaining 1 electron goes to the orbital of next higher energy, that is 2s. Beryllium has 4 electrons. 2 electrons fill the 1s orbital, and the remaining 2 fill the 2s orbital. Boron has 5 electrons. The first 2 electrons fill the 1s orbital. The next 2 fill the 2s orbital, and the 5th electron occupies the 2p orbital. Actually, the 5th electron may occupy any one of the 3 2p orbitals: 2px, 2py, or 2pz, because all have the same energy. However, conventionally we always fill 2px, 2py and 2pz in that order. Carbon has 6 electrons. The first 4 electrons fill the 1s and 2s orbitals. The remaining 2 electrons will go to any 2 of the 3 2p orbitals in accordance with Hund's rule, and these will have parallel spins. Nitrogen has 7 electrons. The first 4 electrons fill the 1s and 2s orbitals. The remaining 3 electrons will go to the 3 2p orbitals in accordance with Hund's rule, and these will have parallel spins. Oxygen has 8 electrons. Fluorine has 9 and neon has 10 electrons. In each of these elements, after filling the first 4 electrons in 1s and 2s orbitals, the remaining electrons enter into next higher orbital, 2p. According to Aufbau principle, they successively occupy the 3 2p orbitals, that is 2px, 2py, 2pz in accordance with Hund's rule. The pairing of 2p subshell starts with oxygen and completes with neon. The electronic configurations of other elements are written in the same way. After filling the 2p orbitals, the electrons fill the 3s and then the 3p orbitals. We can also write the electronic configurations of most of the elements in a simplified manner or condensed form. For example, the element sodium, that has 11 electrons, has 1 electron more than its nearest noble gas, neon. The 11th electron will enter the 3s orbital. Therefore, the electronic configuration of sodium, which is 1s2, 2s2, 2p6, 3s1, 1s2, 2s2, 2p6, 3s1 can also be written in a condensed form as neon 3s1. Similarly, the electronic configuration of magnesium can be written in a condensed form as neon 3s2. Observe how the electronic configurations of elements with atomic numbers 11 to 17 are written in a condensed form in terms of neon. Argon, whose atomic number is 18, has a completed 3p orbital. Therefore, the electronic configuration of potassium, which has 1 electron more than argon, can be written as argon 4s1, where Ar represents the core of noble element argon. The electronic configurations of the atoms generally follow the 3 above said rules for filling up electrons into various orbitals. For example, in potassium, the electrons enter into various orbitals, that is, 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1 in accordance with Aufbau's rule. However, in some cases, the actual configuration differs slightly from the expected ones. The electronic configurations of chromium that has 24 electrons and copper that has 29 electrons do not follow the general trend. The electronic configuration of chromium is expected to be as 1s2, 2s2, 2p6, 3s2, 3p6, 3d4, 4s2, and the electronic configuration of copper is expected to be 1s2, 2s2, 2p6, 3s2, 3p6, 3d9, 4s2. But actually their configurations are 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s1, and 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s1 respectively. This happens in certain elements when two subshells differ slightly in their energies. An electron may shift from a subshell of lower energy to a subshell of higher energy. If this shift results in symmetrical distribution of the electrons in the orbitals of the subshell that has higher energy. The anomaly in chromium is attributed to the fact that half-filled orbital 3d5 has lower energy and extra stability. In copper, the completely filled orbital 3d10 has lower energy and extra stability. The two reasons for the extra stability of half-filled and completely filled subshell configuration are the symmetrical distribution and exchange energy. From the expected electronic configuration of chromium, if one of the 4s electrons shift to the vacant 3d orbital, the distribution of the electrons will become more symmetrical and this will impart extra stability. Similarly, in the expected electronic configuration of copper, if one electron from the lower energy 4s orbital is shifted to higher energy 3d orbital, it will make the distribution of electrons symmetrical and hence will impart more stability. Stability also occurs whenever two or more electrons with the same spin are present in the degenerate orbitals of a subshell. These electrons tend to exchange their positions, and the energy released due to this exchange is called exchange energy. The number of exchanges that can take place is maximum when the subshell is either half-filled or completely filled. As a result, the exchange energy and stability are maximum.